Hello, I'm Olivia, everyone's favorite math teacher. And in today's lesson, we're going to look at my favorite proof of the Pythagorean Theorem. Before we begin with the proof, we are going to need to recall three important things. First of all, what's a right triangle? And a right triangle is any triangle with a right angle. That means it's got a 90-degree angle, one of those perfect corners. We call the sides that make up the right angle the legs, and we call the other side the hypotenuse. So you also need to know, what do all the angles inside a triangle add up to be? We call that the inner angle sum theorem. Well, it turns out that in any triangle, they add up to be 180 degrees. 180 degrees is the same thing as saying pi radians if you're using that kind of measure. And my pi symbol looks a little weird there, but it'll be okay. I think you can understand it. And then the last thing we have to remember is that any right triangle becomes a rectangle if you reflect it on its hypotenuse. Okay? That's going to be really important for the physical proof part, so that we don't have to use algebra when we do this. Now, we are using an equal sign, which of course they didn't really have back when they first were doing proofs like this, but forgive me for it. It just makes things easier than writing out the words. Okay, so anytime you're doing a proof, first thing you need to do is state, what are you proving? Okay, so we are proving that in any right triangle, the sum of the squares on the legs is equal to the square on the hypotenuse. Okay? You may have heard it as this, a squared plus b squared equals c squared. But remember, when you say a squared plus b squared equals c squared, that only works if a and b are the legs and c is the hypotenuse. Okay? So let's go ahead and start with a triangle. Now, I've gone ahead and labeled it on the inside of the triangle. You'll see why in a moment. But this is a triangle with the sides, A being the long side, B being the short side, and C being the hypotenuse, just so that we can stick with convention. Let's go ahead and make 3 more copies of this so that we have 4 total triangles. Now, what we're going to do is we're just going to kind of move these triangles around so that we make a square. So as you can see, all I did was took each triangle and I lined it up so that one side A touched the corner for one side B, and we just did that all the way around. Now, if you look at this, you should notice that we make a square. Every single side of that square is equal to A plus B, that length. And if you look inside that square, it looks like we have another square because we do have a shape that is 4 sides, all with length C. Is that a square? Let's see if we can prove it. So we're going to start by going ahead and labeling the angles we know what they are, okay? So we're going to label the angle with the capital letter of the side that doesn't touch it. So for example, here we have A in the top corner and B in the bottom. So basically every large non-right angle is A, every small non-right angle is B. And if you're having difficulty with that, pause the video and go ahead and, try to make sure that you understand exactly what's going on there, okay? Now, here's the interesting thing. This is a square, which means the sides are a straight line. And if you remember, the straight line has an angle measure of 180 degrees. But we also know that all the angles in a triangle add up to be 180 degrees. So we know that every A plus B has to be 90 degrees because 90 plus 90 is 180. So what that tells us is that on every single side of this triangle, we have an A, we have a B, so to make that a 180 degree straight line, we need a right angle. But if this is a shape that has 4 equal sides and 4 right angles, by definition, it's a square. So that means we have a big square, and inside that square, we have another square that happens to have side length C. We'll come back to that. Let's look at this big AB square, the A plus B square. Let's look at this in another way. So we're going to draw right over the top of it a new square that's the exact same size, and we're going to color it yellow just so that we can tell it apart. Now, I'm going to put little red dots at that joining part for A and B so that we know exactly what the length B is and exactly what the length A is. And notice we haven't really measured anything. We drew this triangle arbitrarily, which means the sides are arbitrary. You could draw this triangle as tall or as short, as big or as small as you want, and this will still be true. That's the power of using letters instead of numbers. Okay, we're proving this generically. So what we're going to do next is we're just going to draw a nice little guideline. And we're going to draw this line so that it starts at one of those connecting points where the A and the B connect, and it's perpendicular to the side of our square. Okay? It's a nice little straight line. It's perpendicular, meaning it makes a right angle. We're not going to draw it in because that's going to kind of clutter up our picture a little bit, and it's already cluttered enough. Okay? But we're only going to draw 2 of these. That's all we're going to need for what we're doing next. Okay? So now let's clean things up a little bit and just look at the yellow square with the red cross in it. And you'll notice that it's a little hard to tell what's going on here with the red A's and B's around because those are for the square. And those correspond to the square with the yellow sides and the red dots, not the inner parts with the red lines. So let's clean that up, and we're going to use a different color. We'll use blue, and we'll just use a blue label to indicate the sides of the shapes inside the square, okay? If you need to, you can go back and see why this is. And if you have a question about it and need something explained, hey, just ask in the comments, okay? I'll be happy to help you out. I'm sure other people would too. So now we have this square, the same square in white and in yellow, but we're looking at it in 2 different ways. So we have the yellow square and we have the white square. The yellow square is made up of 4 pieces, the white square is made up of 5. Okay, so we've got the yellow square and the white square, exact same size. The word we typically use in geometry is congruent. Now, the yellow square is made up of 2 rectangles and 2 squares. So you got a big square and a small square, and then you have 2 rectangles. The white square is 5 pieces, and it's made up of those 4 triangles we used to build it, and then that square in the middle that resulted when we put them all together. Okay? We did all of this, so we know that all of this is true and has been done. Okay? Now, let's look at what exactly this is going to do. Let's label out the area of each piece of both squares. Now, I'm not going to do this laboriously. I'm just going to snap my fingers and voila, there'll be labels. That was not a great snap, but there were labels. Okay? I know it looks a little cluttered, but don't worry. We're going to clean it up in a second. Not the shape, but over here in the middle part. Okay? So just remember real quick, if you don't understand what these labels are, these are simply labeling the area for each shape. So each of our rectangles has an area of A times B, and each of our squares has an area of side times side, or side squared. In this case, B squared and A squared. And then down in our white square, we have the 4 triangles that each have an area formula of 1/2 AB, because they're all congruent, that word we learned earlier. And then we have that littler square in the middle, compared to the big white square, that has a side length of C, so that is an area of C squared. Now, I want to pause a moment here and remind you that when the Greek mathematicians were doing this kind of work, and probably the Egyptian mathematicians and the Aztec mathematicians, and many, many, many of them, this is pre-concept of algebra. So a lot of our math was rooted in the physical world and what we could touch and handle and hold. So for a lot of cultures, the concept of multiplication was the concept of an area, the space inside a flat object. Okay? So that's basically what we're doing here. We're simply writing it in a slightly more modern way, but we're looking at the actual areas of these shapes. And since we know that the white square and the yellow square are the same total area, we know that if we add up the pieces of the yellow square, they have to have the same area as the pieces of the white square. So those 4 yellow bits and those 5 white bits have to add up to be equal. We're going to write that out. Now, this is where, because we're writing it, we're going to do a little bit more algebra than I would like, but don't worry, we're going to manipulate this physically, and you're going to be able to do this with no algebra. But we're going to go ahead and put these together, and we have 2 of those rectangles that are ABs. And if you recall, we said that every pair of those white triangles makes a rectangle. And we even showed that that rectangle had an area of AB. So that means we're going to end up with 2 yellow rectangles that have an area of AB. And if we were to rearrange those white triangles, we'd end up with 2 white rectangles that also have an area of AB. A little more algebra magic, we take away the things that are the same on both sides that are obviously the same because they're both rectangles of AB, keeping everything balanced. And we get that the little square in the yellow square plus the big square in the yellow square is the exact same area as the big square in the white square. And that probably looks very familiar because if we simply flip the A and the B, which we're allowed to do because it's addition, we have the Pythagorean Theorem. A squared plus B squared equals C squared. Or more formally, in any right triangle, the sum of the squares on the legs is equal to the square on the hypotenuse. And you might say, well, wait a second, how does that line up? Well, let's go back a second and look at our yellow square and look at our white square. So C squared is a square that has been built out of the side of the white triangle that is length C. So it is the square on side C of a triangle. And then the little yellow square and the medium yellow square, the B squared and the A squared, well, both of those were built on those same triangles. We simply removed the triangle once we put in the red mark, which means that that's the B side of a triangle, B squared, and the A side of a triangle, the A squared. So the square on B and the square on A is equal to the square on C. Pythagorean Theorem. I hope you liked that proof and that you learned something about the Pythagorean Theorem. As a bonus, see if you can figure out how what we did also proves the square of the sum's polynomial identity. Next time, I'll show you how to do that same proof physically with paper and with no algebra required.